Hello, this is Dr. Tim Webster of the Nova Scotia Community College. I lead the Applied Geomatics Research Group. I thought what I would do is take you through a presentation of what I'm planning to submit to Research Nova Scotia and what I'm asking Pictou County to commit some resources to up front. And if funded, Pictou County will be top of the list in terms of municipalities where this research gets laid out. So I'll share my screen. And pardon me, I'll go back to play the slideshow from the beginning. So the presentation to Research Nova Scotia, the proposal name is Earth, Water, and Fire, Geospatial Analytics Solutions for Climate Variability Effects. This is really focusing in on Research Nova Scotia's climate change and adaptation mission statement that they see problems for Nova Scotia, and I'm proposing solutions. To a lesser degree, there are spin-off products related to coastal development and increased aquaculture, as well as sustainable communities where we're, through land use planning, not putting communities at risk being built in poor places. Basically, the proposal is broken down into 4 pillars. We go from pillar number 1, looking at coastal flooding. There's a whole range of projects built in here, including something called a geoforensic team. I'll explain that a little later. Pillar number 2 is looking at trying to predict river flooding using machine learning and then visualizing that on the internet to show people what could be coming in terms of river flooding. Pillar number 3 is looking at coastal erosion, where we're proposing to both use historical aerial photos to understand what the past erosion rates have been, and then using more modern 3D mapping technology and this TB LiDAR, this stands for topobathymetric LiDAR surveys, to better map the coast and the geomorphology of the coastal zone, and of course this idea of a geoforensic team to get out there after an erosion event to really quantify what happened. Pillar number 4 is looking at wildfires and building a static map of wildfire communities at risk. And this would relate to the amount of conifer fuel and whether there's a fuel break in the proximity to the community. Plus, we're working with an indigenous company known as 3D Wave that has built a system that does wildfire prediction and how that wildfire will move over time. And we see an opportunity there to really enhance that tool. So I can go through each one of these in a little more detail. Pillar number 1 is related to coastal flooding. And right now we've developed this emergency coastal flooding decision support system, but we only have LiDAR mapping done in a few areas throughout Nova Scotia. I want to expand this to the entire province. Essentially how this tool works: we get a storm prediction system 10 days in advance from Environment Canada. We marry that with the predicted tide. Here we have the tide in orange. This is the Pictou Tide Station, and this is Antigonish LiDAR down below. The storm surge is in blue, so they were predicting a 2-meter storm surge ahead of Fiona. This is in advance of Fiona. And then those two add together to give us a total water level. In this case, the total water level was going to be 2.1 meters for the Pictou station. As we move around the chart, the water level actually changes interactively. And we can also use this slider bar to increase the water level to account for waves and so forth. We also can do some GIS analysis where we highlight the amount of roads and highlight where they would be flooded, as well as any critical infrastructure like hospital, ambulance, fire, and seniors' homes. Now, with topobathymetric LiDAR, it allows us to capture elevation of the land and the seabed. And we need that to better understand how a storm surge behaves and how it interacts with the coast. So not only are we showing the water level increasing with a storm surge, those arrows depict the current speeds, how fast the water is moving. And you'll see we're going to inundate over the road over here shortly through this pond and then back out again. So this area is now being inundated, and we can actually look at what the maximum current speed was there. And this, of course, helps us better define the hazard ahead of time. So in addition to the web-based tool, we want to start downscaling the areas that are going to be impacted to do this hydrodynamic modeling, making use of this topobathymetric data we can collect. Similarly, we want to use machine learning to predict river flows, and we want to do that based on weather forecasts ahead of time. We want to use topobathymetric LiDAR data to map more of the rivers. On the right-hand side is an example of River John and Middle River, Cape Breton County, where we've surveyed not only topography, but actually the river channel itself. And this really improves the ability to generate flood risk maps from river flooding. In terms of machine learning, we know that when we get a rain event, we see the river move up in flow and discharge. And then here's another river event, and here's how the river responds. We want to use machine learning to map that and actually figure out and predict what the flow will be. And of course, we need to account for things like snow melt and so forth. And then, of course, once we know the flow, we want to then visualize that on the internet and show how that river is going to flood and what could be flooded with that kind of situation. This is an example of a river cross-section in the middle here, or not a longitudinal profile. So this is along the length of the river. The blue line is the water surface, the black line is the riverbed. So we can see all of the pools that present fish habitat and so forth, and also areas that are going to be tough for fish passage. So it also has some ecological importance and values too, in addition to the flooding. The idea of collect the data once, use it for many things. Now, with respect to being able to map and predict coastal erosion to help municipalities define better land use planning bylaws, here's an example of an aerial photo straight down of before Fiona and after Fiona. And we can see this bank has been eroded somewhat. Now, how do we measure erosion? We can use GPS to do surveys. We can use laser scanning on some vertical features. We can do mobile mapping on a boat or an ATV. Now we're using drones more and more. They've got sophisticated navigation system to give us precise positioning, and we actually have 2 LiDAR units we can put on that drone. Also, we can look back for historical aerial photos to get the historic rates of erosion. And as well, we now have topographic LiDAR, and I'm proposing to collect more topobathymetric LiDAR during this project that also gives us an up-to-date, detailed coastline. And satellite imagery is becoming high enough resolution we can actually map change. On the left-hand side in this slide shows us the traditional way we've mapped erosion in the past. We define a coastline from an image taken at time 1, and then maybe we have a photo at a later time taken at time 2. We measure the same coastline. Then we can look at those coastlines and measure the distance between them by knowing when the photos were taken. We can get a time difference. So we have the distance divided by the difference in time. That gives us the rate of erosion. We often see numbers like 30 centimeters per year in terms of erosion. That might imply that erosion is constant and steady, but in fact it's not. It's an episodic event. We may go years with no erosion, and then one storm, we may lose meters of material and land. Here is, on the right-hand side, is the more modern approach to measure erosion. We can go out and survey a digital elevation model. This is what DEM at time 1 means. This is a mud bank in this area, and this is armor stone in this case. Here is the DEM after a storm at time 2. You can see some of the armor stone's been displaced. What we can now do is something called the difference of DEMs. We can subtract one from the other. And not only can we track how the coastline has moved back, we can actually calculate the volumetric change, how much sediment has been removed. In this case, about 1,800 cubic meters of sediment along a 50-meter section has been removed. Now, when we establish water level sensors and climate stations around the coast, we'll be able to know what the water level was, what the drivers were in terms of the atmospheric conditions, and when we go out and survey, we'll actually know what the wave run-up was by measuring the rack line, the debris line. As we start building this information up from storms, we'll be able to better predict and understand what our coast is made of, if it's a mud bank, it's a cliff, etc. And we'll be able to use machine learning to try to predict for a given storm event how a given coastline is going to react and what we might expect for erosion. Pillar number 4, we're looking at communities at risk of forest fire. And On the right-hand side are the data sets and the approach that's used for the Canadian Forest Service Prometheus system. It's a national-wide system. It uses 200-meter resolution data, very coarse. On the left is an example of the 3D wave product. They've built this for some of the indigenous reserves in the province, but you can only vary the wind and speed direction by these slider bars. We want to actually put in a weather prediction system or a weather forecast, if you will, and see how that fire is going to behave 5 days in advance. And that could give us better information about when a community is going to be at risk and when we need to evacuate people or where we need to shift our resources. I've spoken a couple of times about this geoforensic team to get out there and map events, simulate the event, and then revise these return period statistics. Here, for example, if you remember the Fiona storm surge prediction and total water level, the predicted total water level was 2.1 meters. This doesn't account for waves coming in. Well, at Malagash, it was a little less at 1.6. And I've lost the number here, but it was around 2.1 at Port Hood as well. These yellow numbers are where we've gone out and actually surveyed the high water line. And you'll notice in some cases it's 80 centimeters above, in other cases it's over a meter above. And this is the contribution of wave run-up and the total water level that was captured. These are important values to add in to the statistical calculations of return periods, and often they're not. We're using return periods that were generated in circa 2005. So these storm events are not being incorporated. On the right-hand side, you'll see what that bank looked like we were just looking at in the previous example, before Fiona and after Fiona. And you can see where that 1,800 cubic of sediment has been removed along this 50-meter stretch. On the top, we see the West Hants significant flooding that took place in July. This Meander River eventually burst its banks and swept across here so rapidly with such force and magnitude that it shoved this house off of its footing. And unfortunately, this is where the 4 people got into their vehicle, and unfortunately, their vehicle was pushed and eventually they perished. So we went out here and mapped the high water line of this event. It's important to capture these things so that when you try to model them and better understand them, you know if your model is working correctly. So it's used for validation as well as, again, in terms of updating return periods on river flow. Now, an example of that in the coastal environment is the new provincial coastal flood map that says, here is the projected worst case flooding in the year 2100. Now, in this particular area, we know that Fiona came to a maximum of 2.9 meters. Now, down below is a map we generated as Fiona was approaching, in case maybe the waves were going to have a 1 meter contribution. So now this is a total water level of 3.1, 2.1 from tide and surge, 1 from additional waves. Now, you'll see that this map really agrees with what the province has produced. Very, very similar. So that means that the provincial map that says this is the worst flooding possible in the year 2100, it's only 20 centimeters higher than what Fiona's already done. So that makes it very difficult to convince the public and scientifically defend this map, because I think it's an underestimate. Why is this the case? It's not that the people who made this map made a mistake, but it was the data they were using. And they're using water level storm surge return periods that are outdated and underestimates. And we can go into more detail on that, but we're using data from 2005 that very clearly state, the source states that they don't capture short-lived events like hurricanes and other nor'easters that happen rather rapidly. So these are underestimates, and as a result, our flood maps are underestimates. As we collect more data and map the high water line, we can revise these statistics and improve the storm surge return period level estimates. So, to conclude with the proposal, I've had very positive feedback and response from various stakeholders, whether it's federal government departments, provincial departments, municipalities, research partners in academia, and NGO groups. What will be the result of this if it gets funded? We'll have high-resolution multi-use mapping, improve climate change vulnerability, and as sustainable growth along the coastal zone especially. We'll be able to better track our extreme events and thus refine our statistics. We'll have improved hazard mitigation. Municipalities will be able to conduct better land use planning and be able to defend those plans with their residents. We'll use improved machine learning skills, and we'll be able to map both rivers and coastal erosion projections. We'll have dynamic visualization of hazards, whether it's coastal or river flooding. We'll look at predictions, better interpretation of the data over time, and predictions in real time for river and coastal flooding. Things will be pushed out to the web, so not only the officials can see it, but also the residents. We'll be able to protect our coastlines with better land use planning. And last, we'll be able to achieve world-class research and improved methods in this region. So I'm asking Pictou County to get on board, support me with a $20,000 commitment to this project, and this will make Pictou County be the first county at the top of the list where these data sets and these methods get produced and new products get produced that can be used. So Pictou County will be top of the list for that, for all of these applications, and we'll go quite a bit farther than simply having an erosion, historical erosion rates calculated. So I hope I have your support in this, and I would like to thank you, and hopefully you can make a contribution to this proposal, and we will then keep our fingers crossed, and if so, Pictou County will be at the top of the list. Thank you very much. Happy to answer any questions you have in the future, and happy to answer them by email or another meeting. Thank you.